Good day, everyone. My name is Zhang, and today I will be presenting our study titled Detecting Unit Type Confusion in Component Object Model. In our research, we've covered several unit type confusion bugs within the Microsoft Component Object Model, or COM for short. To begin, let me provide some context about Microsoft COM. COM established a binary interoperability standard, which allow the development of reusable libraries that interact dynamically during runtime. It serves as a foundation for many other technologies like Microsoft OLE and Active and the Windows runtime. Many COM servers operate with high privileges. What makes this situation even more critical is that unit type confusion within COM could potentially be exploited to create a fully reliable exploit. And given Microsoft's significant market share, solving these issues carries a substantial weight. Next, I'd like to take you through the different types of units found in the COM. Broadly, these units can be classified into two main types, customized unit and built-in unit. We further characterize the customized unit into three subtypes. As depicted in the figure, we have the typical unit C, in C language in line 2, which we refer to as a non-encapsulated unit. And unit B, which contains a member of type unit C, is termed an encapsulated unit because one unit is wrapped with another unit. Then we have unit A that has a member of type unit B. This is interesting because it implicitly contains a unit, so we call it as re-encapsulated unit. Besides this, COM also outlines two built-in units, the variant and the provariant. As illustrated in the figure on the right, based on our analysis, each version of the Windows operating systems boasts over 10,000 distinct types of units within its COM. And what's more, over half of all customized units in COM consist of both pointer and non-pointer members. This is particularly concerning because type confusions in such units could result in severe problems. And moving forward, let's dive into the concept of unit type confusion. And please refer to the figure that depicts a simple program with unit type confusion vulnerability. Here, a unit meta infer is defined in line 4 to 7, whose member can either be an integer or a string pointer. And in line 9 to 12, the structure user infer possesses a unit member named infer. Another member type characterizes the data type of the infer. And when it equals to 1, it should be a string pointer, for example. And in line 19, the term users refer to an array of the user infrastructure containing the names and the IDs of the two users. Nevertheless, there is a point of concern in line 23, where the code straightforward treat each entry as a name entry and print it as a string pointer in line 15. So this is a simple unit type confusion which could trigger a program crash. The type confusion occurs because an integer is interpreted as a pointer, and the root cause is that the type unit member is not properly checked before being used. Now let's dive in deeper into the unit type confusion within COM. COM operates in a server-client model where the COM server exposes certain interfaces that the client can invoke. Specifically, when an interface function accepts unit parameters, a client can parse the unit to the server process in this way. And if a unit type confusion vulnerability exists in the COM server now, this action can directly trigger it. Consequently, an ordinary COM client has the potential to activate high privilege bugs in server side. However, there is a safeguard within COM that stops clients from passing an arbitrary unit descriptor. This is marshalling process. Each request along with its parameters will be marshaled firstly before being sent to the server. And this process packages the unit member in accordance with the descriptor. Therefore, if the server outlines the unit member before checking the descriptor, no unit type confusion occurs. And conversely, if descriptor verification is bypassed, server could encounter unit type confusion. And taking a step further, we can detect unit type confusions by verifying whether have the server checked the descriptor properly. We summarize our contribution as follows. We firstly analyze the different form of units in Windows COM and how they result in the creation of unit type confusion. And we create a confusion, a novel framework to detect unit type confusion in COM. And we analyzed more than 79,000 COM objects and found 36 unit type confusions and exposing 4 confirmed CVEs. Now let's move on to the detail of our framework confusion. It contains 4 main steps, which I will outline next. The first step involves the extraction of COM objects. During this phase, we aim to export 3 crucial elements. The first one, the MIDL file, the Microsoft Interface Definition Language files, which contains the customized union and interface function declarations. And the figure on the right shows an example of the exported MIDL files. And the COMServer binary is the second thing, which implements the COMServer. And the third one is the interface function table, which stores the addresses of each interface function implementation. And the second step is to categorize the different type of customized units in MIDL files. We construct a directed acyclic graph to achieve that. And each node in the graph signifies a structure, and an edge from U to V indicates that the structure U includes a member of type V. The normal units are non-encapsulated units, and the parent nodes of the normal units are encapsulated units, and their ancestor nodes are re-encapsulated units. The third step is to locate unit variables in the binary. We choose to use taint propagation to locate them. We start our taint propagation from the interface function that take units as parameters. For example, process 4 and process 5 in this figure serves as a starting point as they take units as parameters. During taint propagation, we separately taint the unit descriptor and the unit member. And additionally, we identify 3 different types of functions and apply unique taint strategies for each. And finally, to avoid path explosion, we establish the 3 thresholds that, when reached, halt further analysis. Next, we've introduced how to identify unit type confusions. Our checking strategy is to calculate possible values of unit descriptors when unit member is used. If there are more than 1 possible values, we flag them as potentially vulnerable. To perform this, we deploy symbolic execution. We firstly initialize the parameters of the interface function object based in the declaration found in the MIDL files. And for the special this object, which normally exists in the C++ program, we currently initialize it as a symbolic object with a length of 16 kilobytes. In practice, we symbolically execute the program along with the taint propagation. Additionally, we prune some branches if we discover that the unit descriptor can only hold 1 value in that specific branch because it is safe. And the final question is how to define use. We consider a unit member to be in use when it is a parameter of a not analysis function, or it is the target address of a memory access operation, or it is an operand of comparison or arithmetic instructions. Now, let's move on to evaluating confusion. The first question is, how effective is confusion in analyzing COM binaries for sensitive interface function? And as the table indicates, we examined more than 79,000 COM objects across 3 popular Windows releases. And through this process, we identify a total of 3,940 sensitive interface functions. The second problem is how precisely can confusion identify unit type confusions? As illustrated in the figure, we have totally found 78 unit type confusion with 42 false positives, and the 36 true positives include 19 confusion of pointer and 17 confusion of non-pointers. The third issue is how are the false positives generated? We have classified false positive into 3 categories. Firstly, some parameters have in-out attributes, but only the out take effects. And secondly, we sometimes inaccurately infer the number of arguments of a function. And lastly, as shown in the figure, some discriminant checking is affected by wrongly assigned symbolic variables. And the last problem is, how dangerous are those unit type confusion bugs? Can they cause severe damages? As shown in this figure, we have totally found 19 confusion of pointers, which can directly trigger memory error and exposing 4 confirmed CVEs. In conclusion, we propose the confusion and the first tool for discovering unit type confusion vulnerabilities in Windows COM. And confusion applies taint analysis and symbolic execution based on the MIDL files to identify unit type confusion in COM. Confusion analyzed more than 79,000 COM objects and discovered 36 unit type confusions, and of which 4 run in high privilege services and are now given 4 CVE identifiers. Thank you all for your attention at the time, and I'm open to any questions and discussions you might have. Thank you.